The array sizing of a PV system includes the choice of a PV module model and an inverter model. Then, the number of modules in series within a string, the number of strings in parallel, and the number of MPPT inputs to the inverter must be defined. In this tutorial, we will explore the array sizing tool, which helps to define these numbers correctly. Start by opening a grid-connected system and open the residential demo project. We will work with the first variant, VC0. Click on System. In order to show some of the features of the array sizing tool, let's click on No Sizing. In this project, we are using 300 watt peak modules and a 7.5 kilowatt inverter. This simple system contains one subarray. More complex systems can contain several subarrays. Recall that the gray frame defines the characteristics of the subarray. Modules in series in a string and number of parallel strings are defined in green and blue here. Click on Show Sizing to open the array sizing tool. This tool will help to contextualize the consequences of the array size that you choose. This tool concerns the subarray that is currently being edited. A first graph shows the voltage constraints, which will determine the number of modules that can be connected in series. Here you have the PV array IV curves. Both curves correspond to an irradiance of 1000 watts per square meter. The curve shifted to higher voltages represents winter conditions when operating around 20 degrees Celsius. The curve shifted to lower voltages represents summer conditions at 60 degrees Celsius. The open circuit voltage at the lowest possible temperature is also shown with this pink point. This temperature is defined as -10 degrees Celsius here. These sizing temperatures are defined in the project settings. These are just orders of magnitude for the sizing evaluation. These may be updated according to the weather conditions of your site, but most of the time, you can just leave them unchanged. Only the lower temperature for defining the higher VOC should be adapted to your local conditions. These temperatures are cell or array temperatures, not ambient temperatures, except for the lower temperature for absolute voltage limit, which is an ambient temperature, to account for the worst-case scenario. These temperatures are only useful for defining the number of PV modules in series during this sizing process. They are not involved in the simulation in any way. The graph shows the lower and higher operating voltage limits of the inverter. Ideally, the MPP values of the summer and winter IV curves should lie between these limits, but this is not a strict condition. Exceeding these limits will likely result in over or under voltage losses in the simulation. The graph also shows the absolute maximum DC voltage that is allowed at the inverter input in pink. The VOC at -10 degrees Celsius should not exceed this maximum. This is a mandatory condition, since exceeding the absolute maximum voltage could lead to serious damage to the inverter. This is specified in the IEC standards. Change the number of modules in series to see how the curves change with respect to the limitations. Notice that PVsyst proposes limits for the number of modules in series. Here, the limits are between 6 and 21. If you exceed these limits, you can see that one of the design rules described before has been broken. The graph also shows the input current and power limitations for the inverter if specified. Don't worry about this too much. These are not really significant, as the inverter takes care of its own limitations during operation. As you change the number of modules in series, pay attention to the messages in the blue box. Orange messages are warnings that the system isn't optimized. Red messages are errors in the design, and this will stop you from being able to perform a simulation. Next, we can consider the number of strings in parallel, which will determine the array power. For this, PVsyst shows the distribution of the energy generated as a function of the array power for the whole year. Each bin in this histogram represents the total energy produced during the year when the system is operating between the two power values. For example, 250 kilowatt hours will be produced throughout the year when the system operates between 4 and 4.2 kilowatts. This distribution depends on the weather data and plane orientation. The violet arrow of the histogram shows the nominal power at the input of the inverter. The operating conditions above this value will be limited. Currently, there is very little energy produced from the power levels beyond the violet line. However, if we increase the number of strings, you will see the green curve shift to the right as it produces more power. If it goes beyond the nominal power of the inverter, a violet curve appears below the green curve. This violet curve represents the limited power effectively produced by the inverter in clipping conditions. Also notice that in the array voltage sizing plot, the maximum power points of the IV curves are greater than the inverter maximum power. The green curve shows the total available power from the array if the array is working at its maximum power point. The differences between these curves represents the overload loss. This loss is displayed above the power characteristics. By default, PVsyst sets an overloss limit of 3%. If the overload loss is between 0.1 and 3%, PVsyst considers the inverter to be slightly undersized and displays an orange warning. In this case, PVsyst will still allow you to run the simulation. If the overload exceeds 3%, PVsyst gives an error message in red and the simulation is not possible. If you want to simulate systems with a highly oversized PV array, you can increase the limit of 3% in the project settings. As we just showed, you can modify the overload loss by changing the number of modules in series or strings in parallel. However, you can also modify this by changing the number of inverters. An important indicator for the system size is the nominal power, or Pnom ratio. This is often called the DC-AC ratio. Proper sizing corresponding to an overload loss less than 3% usually leads to a Pnom ratio between 1.25 and 1.3. Note that the overload loss calculated by the simulation may be significantly different from this sizing value. The overload loss calculated in the sizing tool is a rough approximation that cannot take all of the system losses into account. The overload loss in the final report will be the result of the detailed hourly simulation. It is usually lower than the estimation given here in the array sizing tool. One final note on the histogram shown below is the orange line representing the maximum modules area, if this was defined as a sizing constraint. In the system definition, we've set the maximum area to 50 square meters. Therefore, the position of this line with respect to the array power also shows when the number of panels in the array exceeds this area. In this tutorial, we discussed the array sizing tool. This tool assists you in sizing your PV array, that is, defining the number of modules in series and the number of strings or inverter inputs. It also contextualizes why a given PV array is improperly sized for a given system.